So here are the solutions to quiz 4. I asked you first of all to draw a Freebody diagram for the rocket while the motor was burning, label all forces, and subscript them with object and agent. So here's the ramp, inclined upwards at angle theta. There are 4 forces acting on the rocket. The thrust of the rocket upwards, up the ramp, which is in the positive x direction. Here's my coordinate system. The normal force of the ramp acting on the rocket in the plus y direction. The frictional force acting down the ramp. And then lastly, the weight acting vertically downwards. But what I do here with this tilted coordinate system is to take the component of the weight perpendicular to the ramp, mg cosine theta, and parallel to the ramp, mg sine theta. Each force has a subscript indicating the object, which is always little m. That stands for the rocket and whatever the agent is. So for the weight, the agent would be the Earth. For the thrust, the agent is the rocket. For the normal force, the agent is the incline, and for the frictional force, the agent is the incline. So next thing to do is to write down Newton number 2 in the x direction and the y direction, keeping the coordinate system in mind that I have on the previous slide. And so the mass times the acceleration in the x direction is the net force in the x direction, which there is a positive rocket thrust, negative frictional force, and a negative component of the downward weight in the direction of the parallel to the ramp. Same thing for the y direction. There's a positive normal force, a negative component of the weight in perpendicular to the ramp, and since the acceleration in the y direction is 0, the normal force minus mg cos theta is equal to 0. The only unknown force is the normal force, and from Newton number 2 in the y direction we can conclude that the normal force is mg cos theta, 0.8 kgs times 10 meters per second times the cosine of 15 is 7.73 newtons. Solve for the acceleration of the rocket up the ramp. So we take the Newton number 2 equation and solve for a sub x. That gives this equation right here. Always better to keep things symbolic and then put the values in at the end. And so a sub x is plugging the values in, 25 newtons for the rocket thrust minus 0.5 newtons for the friction divided by the mass of the rocket, 0.8 kgs, minus g sine theta, 10 meters per second times the sine of 15, and that works out to be 28.0 meters per second. Draw an FBD for the rocket at t equals 4 seconds, and so that's going to be the previous FBD, but without the rocket thrust in there because the rocket motor has burned out. So now there are 3 forces acting on the rocket, and if we then take this a sub x that we had for the previous burn phase of the rocket and set the rocket thrust equal to 0, that would give us 0.5 newtons divided by 0.8 kgs minus 10 meters per second times the sine of 15 is, well, minus 3.21 meters per second is what the acceleration is during the glide phase after the rocket is burned out. What is the velocity of the rocket at 4 seconds? So to answer that question and the next one, how far up the ramp the rocket goes, I drew a v versus t graph. During the first 3.5 seconds, that graph would be a straight line that goes upward with a slope of 28 meters per second. That's the a sub x we computed from Newton number 2. And for 3.5 seconds then that would give a velocity at the end of the boost or burn phase of 28 meters per second times 3.5 seconds, which is 98 meters per second. I'm using kinetic equation number 1 here. Then in order to get the velocity at 3.5 seconds during the glide phase, and we're half a second into that, we can take 98 meters per second as the initial velocity and use kinetic equation number 2 and conclude that at 4 seconds the velocity is 98 meters per second minus 0.5 seconds times the 3.21 meters per second acceleration, which gives 96.4 meters per second at the end at t equals 4 seconds. Now to see how far up the ramp goes, we're going to need the area under these two triangles. And so the first triangle, we're all set. We can calculate the area as 1/2 the base times the height, which is 1/2 times 3.5 seconds times 98.0 meters per second. That's the velocity at the end of the burn phase. And now to get the area under the second triangle, we first of all need to find the time elapsed from the end of the burn phase to when the rocket gets to a v sub x of 0, which is going to be the highest point it reaches on the ramp, the turning point. And to do that, we then use kinematic equation number 2 to set the velocity of the rocket in the x direction to 0 and set that equal to the initial velocity at the beginning of the glide phase, which is 98 meters per second, minus t times the acceleration during the glide phase, which is 3.21 meters per second. I put the minus sign out front here. So I can solve for t and then conclude that the glide phase is 30.5 seconds. Now I can compute the area under the second triangle, which is 1/2 the base times the height, 1/2 times 30.5 seconds times 98 meters per second, which works out to be 1495 meters. So you can see that this is definitely not to scale. The area under the glide phase triangle is much greater than the area under the boost phase triangle. So how far up the ramp goes is then the sum of these two areas. The first one representing the displacement up the ramp during the boost phase, the second representing the displacement up the ramp during the glide phase. And so that gives 1667 meters, which to 2 sig figs is 1.7 kilometers. Question 2 started with a question about a fisherman pulling a fish out of the water, where we're going to ignore drag from either the water or the air. And so the fish is accelerating upwards in this direction. There is, I didn't draw the coordinate system here, but I'm assuming a plus y-axis pointing in the upward direction. And then the second force acting on the Newton is, of course, its weight, which is mg. And so from Newton number 2, we know that mass times acceleration is equal to the net force, ma equals t minus mg. So I can solve this for little m, that's the mass of the fish. It's, little m is the tension divided by a plus g. Well, I know that t is bigger than or equal to 22 newtons because the line broke, and therefore I know that m is bigger than or equal to 22 divided by 13 meters per second, again using easy numbers for little g, which comes out to be about 1.7 kgs. Okay, so the rest of the test was about the cone and the drag force. And so I asked for a free body diagram before and after terminal velocity. Before terminal velocity, the cone is accelerating downwards. By Newton number 2, that means that the upward drag force is smaller than the downward weight, mg. After terminal velocity, the acceleration is 0, which means d has the same magnitude as mg and the net force is 0. I asked you to then draw a coordinate system, and based on measurements we do in class and things that I told you, to come up with an estimate for big C. Big C is the drag coefficient in the equation. D is equal to 1/2 C rho A V squared. So first of all, we had a circle 5 centimeters in diameter with 1/4 cut out, and so the mass of the cone is going to be since I told you that the area that the mass for an 8.5 by 11 sheet of paper was 5 grams. The mass of the cone is 3/4 pi r squared, but r is 5 centimeters. And so the mass of the cone is going to be the ratio of the area of the cone, that's this, to the area of the sheet of the paper. There is a typo here. That should be 11 inches, 8.5 by 11. This number is right, but that number isn't. Times the mass of the sheet of paper, which is 5 grams. So in kilograms, that's 5 times 10 to the minus 3 kgs. So 3/4 times pi r squared divided by 8.5 by 11 inches converted to square centimeters, and so one can do that by multiplying by 2.5 centimeters over inches squared, gives 4.9 times 10 to the minus 4th kgs. And again, this should be 11. This number is correct. That number is not. So that gives me the mass of the cone, and so the projected area then is this smaller circle that you get if you fold the cone edge to edge, as you saw in class, and then you look at the cone with the vertex pointing down. That area is the area of a circle that has a radius of 3/4 of 5 centimeters. And the reason you know that is because you know the circumference of this circle enclosing the projected area is 3/4 of 2 pi times 5 centimeters, and therefore that could be rewritten as 2 pi times 3/4 times 5 centimeters, which implies that the radius of this projected area is 3/4 times 5 centimeters. So the projected area is pi r squared, but r is now 5 centimeters, 3/4 of that squared. And I'm now going to convert from square centimeters to square meters by multiplying by meters over 10 to the 2 centimeters squared, which gives 4.42 times 10 to the minus 3 meters squared. So now, after terminal velocity has been achieved, using the second of the two Freebody diagrams on the other page, mg minus 1/2 c rho a projected vt squared is equal to 0. Since the net force is 0, I can solve this equation for big C. Big C is 2 times the weight of the cone divided by the air density times the projected area times the v sub t squared. When we did the experiment in class, v sub t was estimated to be 2 meters divided by 1.4 seconds, which is 1.43 meters per second. So we can put that in for this, and what we get is big C is 0.89. And if you look at the units, kilograms cancel, seconds to the minus 2 cancels, and you end up with meters on top and meters on the bottom. And so big C is dimensionless. So the estimate I arrived at, and you should have gotten something close, is 0.89 for big C. Okay, last question. Can you predict what the drag coefficient what the drag coefficient for the cone would be if the radius of the initial circle on the flat paper were doubled. Okay, so that would mean big R would go to 2R, which would mean that the area would be 4 times as big. Well, if the area is 4 times as big, that means the mass is going to be 4 times as big. But since the shape is unchanged, big C is unchanged. That doesn't change. More interestingly, the V sub t, the formula for V sub t, you could solve for V sub t in the above equation and get 2 times the weight divided by C rho A projected. And since M gets scaled up by a factor of 4 and A does 2, the ratio remains the same, and that tells you that the terminal velocity is unchanged. If you do a scale up of 2 on the cone.